Dear friends and colleagues, it is my real pleasure to be here. I was so fortunate that I attended the first and second Cermak, and I remember many interesting details of that, and I'm very glad that this Cermak7 happened and that we have Cermak himself with us. I have so many real happy memories with him. Now, my title is a little bit similar than the subject of this conference, but I restrict my talk to the continental lithosphere. So, of course, we all know this, how important thermal processes are, how the temperature distribution is affecting all these. And of course, the continental lithosphere is a key element of plate tectonics. In the following, I concentrate on the temperature field, 2D, 3D, and of course the geothermals, which is a common working tool also for petrologists, as we have heard today. And so this is the subject. Okay, what real experimental data do we have from deep temperatures? Practically nothing. At 2 points on the air surface, we have temperatures at great depth. You know all this. This is the no pointer.
This one.
Aha. If I do it, it doesn't work.
Okay, it's there. Just in this one. Und einfach vielleicht ein bisschen stärker drücken. Okay. Yeah.
Ah, yeah. Okay, this is the cola, and this is the KTB. This went down to 12, this went down to 9 kilometers. These are the data we have, of course. This is a rather straight geotherm. This is also after all the corrections you have to make for the equilibrium. But these temperatures, 2213 and 260, are the only deepest data points. Well, what can we do? Of course, we can estimate by calculations, and in the following, I concentrate on this. Okay, how to calculate these temperatures? You know, you need ingredients, you need, I'm unable, yeah. Anyway, you know the ingredients, the temperature at any depth Z you can calculate. You have your input parameters, the surface heat flow, the thermal conductivity, and the heat production. Well, of course, you must have this input data. The thermal conductivity is depending on Rob type, but fortunately it's within a rather narrow scale. It's maybe a factor of 2 or 3 differences. On the other hand, the radioactive heat production, this can vary over 2 orders of magnitude. So let's see this detail. Well, where to take this heat production from great depth? Well, there are some boreholes, there are some materials, but fortunately, an empirical relationship was once developed to use seismic VP velocities, which can be measured by refraction profiles to great depth. Many such data exist. And if you have the seismic velocity, then you just go and determine the radioactive heat production. And the higher the seismic velocities, the lower is the heat production. And this relationship I was fortunate to develop, empirical relationship, in 1973. And I'm very, very sorry that the next planet speaker, Derek Asteruk, is not here, because he confirmed in a paper with his colleague Webb this empirical relationship with thousands of measured data. Okay, so if you need somewhere in the subsurface the heat production, you look for VP values, and then you can have. Actually, this relationship has been also discovered by Russians, but fortunately a couple of years later. But they did it apparently independently. Okay, so let's go ahead. When you go to calculations, we have seen what input data you need, and surface boundary condition also everybody knows. Then you can calculate, for example, for a horizontal 2D situation, you just have to use the thermal conductivities lambda and the thermal conductivities lambda and the heat production A. Anyway, so this is the analytical modeling. The numerical modeling, you all know, there is nowadays really sophisticated. The only thing you really need are reliable input parameters. So this is really now a state of the art. Many elements can be treated, millions of elements, and of course, to have this inserted, there are these really useful automatic mesh generators. Okay, I will show examples. First, near home, the Swiss Central Alps. Then we go to Scandinavia, and finally in the USA. Okay, I'm very impressed by this paper. It is by Spooner et al. And the second author, Magdalena, was here yesterday, but she's unable to come. And they really made a 3D thermal field calculation with many nodes, as you see, using this software. And the lower boundary was the LAB, the lithospheric boundary. So let's see what they got. It's impressive how big their area was. 500 per 500 kilometers and 100 kilometers down to depth. And they show their results, the temperature results, in two profiles. And actually, their work was to see a relationship between temperatures and seismicity. The red dots are earthquake foci. So now we look at this cross-section, especially its crossing point. This is right in the Swiss Central Alps. So this is this profile, and you see the boundaries and also the isotherms, and especially the 275, the 450, and the 600 isotherms. And here, this profile really got interested me. This paper is from 2020, but then I remembered I did such calculations already in the 70s, so I was really wondering how this fits. Now, let's concentrate on, concentrate on these data points, the 275, 460. Okay, now, this is my geotherm. It was published in 75, of course, in German, and also, of course, in the old units. So thermal conductivities are calories per centimeter. The heat flow is in calories per square meter and second, and heat production is calorie per cubic centimeter and gram. Here are the numerical data which I took, but apparently I took this data, this numerical data, quite fortunate, because these are the results of Spooner et al. So either they were lucky or I was lucky, but I was certainly happy. Okay. Now, next example is from the northernmost segment of the famous European geotraverse. The European geotraverse went from Tunisia to the North Cape, and we modeled this in 2D. And here you see input parameters. This is the seismic profile of the VP velocities. And these are the heat productions which were then derived by this empirical relationship. And the results are here, the Moho heat flow, for example, and especially this bulging of the isotherms and this special place. And in a publication of Gugigsberg and Bertelsen, these are petrologies that I talk about sublithospheric agglutination. Well, I cannot make any details, but they apparently explain this bulging. Now, in the following, and the rest more or less, I go to the lithosphere thickness. Of course, here we go into issues like solidus, liquidus. For example, the solidus is the boundary between various stress fields, so brittle above, ductile below, and when you have the liquidus, then below the liquidus, the rock is molten. And it was already mentioned that the intersect of the solidus with the geotherm can define the lithosphere asthenosphere boundary. And one of the most important assumptions in all these calculations is that we have only conductive heat transfer. Also, the Spooner paper used the calculations for heat conduction alone, and usually only below the LAB are other heat transfer mechanisms like convection and even at higher temperatures radiation. Yeah. Okay. I think I will get it. Of course, the higher the heat flow, the steeper the geotherm. The high heat flow, let us think about thinner, lower heat flow, thicker lithosphere, and of course, a thick, cold lithosphere is rather inert in terms of plate tectonics. Okay, just one example. This is by Pollack and Sass from the US. This is a quite famous paper, and I was really happy to include it in this book. I was able to edit with Heinel and Stegener. This is the Handbook of Terrestrial Heat Flow. It's also well known, certainly also in the Heat Flow Commission. Anyway, let's go to this paper of Pollack and Sass. They looked into 4 provinces in the US, and this is the Sierra Nevada. This is the coldest geotherm. Then the stable, the main part of the North American continental lithosphere is stable, and then are more hot and more surface heat flow, basin and range. You know, even the bottom mountain high is with quite high heat flows. This is the surface heat flow, this is the mantle heat flow, 50 in this case. And these are the solidus and liquidus curves in the view of Pollack and Sass. I'm not so happy that they think that the continental lithosphere has basalt. This is rather reserved for the oceanic lithosphere. But certainly the solidus curves are certainly right for diorite and granodiorite. Now, I take this figure over into the next figure. The previous figure is this. And now we go much deeper. You see, 250 kilometers. And now I try here with these tools to determine the lithospheric thickness, and assuming that we have peridotite down here. Then, if I go now to this peridotite, and there are 3 options: dry, mixed volatile, and hydrous. And I go to mixed volatile and take the surface heat flow of 50. Then I am in this geotherm, and then I go to the crossing point, and then this is the lithospheric thickness. Okay. With this, I go to some further, but only very few other examples. These are assembled in a book which I fortunately co-edited with Vladimir Cermak, and the title is Terrestrial Heat Flow and the Lithosphere Structure. And in this book, which is 500 pages, we have oceanic and also terrestrial lithosphere. They are examples of lithospheric structure and geothermics, Aegean Sea, Central Europe, Asia, Pacific, Canada, China, and so on and so on. So we are very fortunate already at this time having assembled all this information about the continental level. In my abstract, there was mentioned the xenoliths and seismic tomography for lithospheric studies. Of course, I cannot go into the detail, but there is this paper published in a summer school, and if you Google it, then you can have it. And the conclusions, I don't have to repeat what I said. These are the conclusions. My only thing I would like to say, that when you make the modeling, you have to take reliable data, and this database is still to be expanded, and you are working on this, and certainly this will bring the results which are needed.